Accuracy, precision of instruments, and errors in measurement. Measurement is the foundation of all experimental science and technology. The result of every measurement by any measuring instrument contains some uncertainty. This uncertainty is called error. Every calculated quantity which is based on measured values also has an error. We shall distinguish between two terms, accuracy and precision. The accuracy of a measurement is a measure of how close the measured value is to the true value of the quantity. Precision tells us to what resolution or limit the quantity is measured. The accuracy in measurement may depend on several factors, including the limit or the resolution of the measuring instrument. For example, suppose the true value of certain length is near 3.678 cm. In one experiment using a measuring instrument of resolution 0.1 cm, the measured value is found to be 3.5 cm, while in another experiment using measuring device of greater resolution, say 0.01 cm, the length is determined to be 3.38 cm. The first measurement has more accuracy because it is closer to the true value, but less precision because its resolution is only 0.1 cm, while the second measurement is less accurate but more precise. Thus, every measurement is approximate due to errors in measurement. In general, the errors in measurement can be broadly classified as A. Systematic errors and B. Random errors. Systematic errors. The systematic errors are those errors that tend to be in one direction, either positive or negative. Some of the sources of systematic errors are A. Instrumental errors that arise from the errors due to imperfect design or calibration of the measuring instrument, zero error in the instrument, etc. For example, the temperature graduations of a thermometer may be inadequately calibrated. It may read 104 degrees Celsius at the boiling point of water at STP, where it should read 100 degrees Celsius. In a vernier calipers, the zero mark of vernier scale may not coincide with the zero mark of the main scale, or simply an ordinary meter scale may be worn off at one end. B. Imperfection in experimental technique or procedure. To determine the temperature of a human body, a thermometer placed under the armpit will always give a temperature lower than the actual value of the body temperature. Other external conditions such as changes in temperature, humidity, wind velocity, etc. during the experiment may systematically affect the measurement. C. Personal errors that arise due to an individual bias, lack of proper setting of the apparatus, or individual's carelessness in taking observations without observing proper precautions, etc. For example, if you by habit always hold your head a bit too far to the right while reading the position of a needle on the scale, you will introduce an error due to parallax. Systematic errors can be minimized by improving experimental techniques, selecting better instruments, and removing personal bias as far as possible. For a given setup, these errors may be estimated to a certain extent, and the necessary corrections may be applied to the readings. Random errors. The random errors are those errors which occur irregularly and hence are called random with respect to size and sign. These can arise due to random and unpredictable fluctuation in experimental condition. Example, unpredictable fluctuations in temperature, voltage supply, mechanical vibrations of experimental setups, etc. Personal unbiased errors by the observer taking readings, etc. For example, when the same person repeats the same observation, it is very likely that he may get different readings every time. Table 2.5 Range and order of time intervals. Lifespan of most unstable particle 10 power minus 24 seconds. Time required for light to cross a nuclear distance 10 power minus 22 seconds. Period of X-rays 10 power minus 19 seconds. Period of atomic vibrations 10 power minus 15 seconds. Period of light wave 10 power minus 15 seconds. Lifetime of an excited state of an atom 10 power minus 8 seconds. Period of radio wave 10 power minus 6 seconds. Period of sound wave 10 power minus 3 seconds. Wink of eye 10 power minus 1 second. Time between successive human heartbeat 10 power 0 second. Travel time for light from moon to earth 10 power 0 second. Travel time for light from sun to earth 10 power 2 second. Time period of a satellite 10 power 4 second. Rotation period of the earth 10 power 5 second. Rotation and revolution periods of moon 10 power 6 second. Revolution period of earth 10 power 7 second. Travel time for light from nearest star 10 power 8 second. Average human lifespan 10 power 9 seconds. Age of Egyptian pyramids 10 power 11 seconds. Time since dinosaurs become extinct 10 power 15 seconds. Age of the universe. Least count error. The smallest value that can be measured by the measuring instrument is called its least count. All the readings or measured values are good only up to this scale. The least count error is the error associated with the resolution of the instrument. For example, a vernier caliper has a least count as 0.01 cm. A spirometer may have least count of 0.001 cm. Least count error belongs to the category of random errors, but within a limited size. It occurs with both systematic and random errors. If we use a meter scale for measurement of light, it may have graduations at 1 mm division scale, spacing or interval. Using instruments of higher precision, improving experimental techniques, etc., we can reduce the least count error. Repeating the observation several times and taking the arithmetic mean of all the observations, the mean value would be very close to the true value of the measured quantity. Absolute error, relative error, and percentage error. A. Suppose the values obtained in several measurements are A1, A2, A3, etc. till AN. The arithmetic mean of these values is taken as the best possible values of the quantity under the given conditions of measurement, as A mean equals A1 plus A2 plus A3 plus so on till AN divided by N, or A mean is equal to summation of I runs from 1 to N AI divided by N. This is because, as explained earlier, it is reasonable to suppose that individual measurements are likely to overestimate as to underestimate the true value of the quantity. The magnitude of the difference between the individual measurement and the true value of the quantity is called the absolute error of the measurement. This is denoted by modulus of delta A. In absence of any other method of knowing true value, we consider arithmetic mean as a true value. Then the errors in the individual measurement value from the true value are delta A1 equals A1 minus A mean, delta A2 equals A2 minus A mean, so on till delta AN equals AN minus A mean. The delta A calculated above may be positive in certain cases and negative in some other cases, but absolute. B. The arithmetic mean of all the absolute errors is taken as a final or mean absolute error of the value of a physical quantity A. It is represented by delta A mean. Thus, delta A mean equals modulus of delta A1 plus modulus of delta A2 plus modulus of delta A3 so on till modulus of delta AN whole divided by N, which is equal to summation I runs from 1 to N modulus of delta AI divided by N. If we do a single measurement, the value we can get be in the range of A mean plus or minus delta A mean. That is, A equals A mean plus or minus delta A mean, or A mean minus delta A mean is less than or equal to A, which is less than or equal to A mean plus delta A mean. This implies that any measurement of a physical quantity A is likely to lie between A mean plus delta A mean and A mean minus delta A mean. C. Instead of the absolute error, we often use the relative error or the percentage error delta A. The relative error is the ratio of the mean absolute error delta A mean to the mean value A mean of the quantity measured. Relative error equals delta A mean divided by A mean. When a relative error is expressed in percent, it is called percentage error, small delta A. Thus, percentage error small delta A equals capital delta A mean divided by A mean. Combination of errors. If we do an experiment involving several measurements, we must know how the errors in all the measurements combine. For example, mass density is obtained by dividing mass by the volume of the substance. If we have errors in the measurement of mass and of the sizes or dimensions, we must know what the errors will be in the density of the substance. To make such estimates, we should learn how errors combine in various mathematical operations. For this, we use the following procedure. A. Errors of a sum or a difference. Suppose two physical quantities A and B have measured values A plus or minus delta A, B plus or minus delta B respectively. where delta A and delta B are their absolute errors, we wish to find the error delta Z in the sum. Z equals A plus B. We have by addition Z plus or minus delta Z equals A plus or minus delta A plus B plus or minus delta B. The maximum possible error in Z, delta Z equals delta A plus delta B. For the difference, Z equals A minus B. We have Z plus or minus delta Z equals A plus or minus delta A minus B plus or minus delta B equals A minus B plus or minus delta A plus or minus delta B, or plus or minus delta Z equals plus or minus delta A plus or minus delta B. The maximum value of the error delta Z is again delta A plus delta B. Hence the rule, when two quantities are added or subtracted, the absolute error in the final result is the sum of the absolute errors in the individual quantities. B. Errors of a product or a quotient. Suppose Z equals A into B and the measured value of A and B are A plus or minus delta A and B plus or minus delta B. Then Z plus or minus delta Z equals A plus or minus delta A into B plus or minus delta B, which is equal to AB plus or minus B delta A plus or minus A delta B plus or minus delta A delta B. Dividing LHS by Z and RHS by AB, we have 1 plus or minus delta Z by Z equals 1 plus or minus delta A by A plus or minus delta B by B plus or minus delta A by A into delta B by B. Since delta A and delta B are small, we shall ignore their product. Hence the maximum relative error delta Z by Z equals delta A by A plus delta B by B. You can easily verify that this is true for division also. Hence the rule, when two quantities are multiplied or divided, the relative error in the result is the sum of the relative error in the multipliers. C. Errors in case of measured quantity raised to a power. Suppose Z equals A square. Then delta Z by Z equals delta A by A plus delta A by A equals 2 into delta A by A. Hence the relative error in A square is 2 times the error in A. In general, if Z equals A power P into B power Q divided by C power R, then delta Z by Z equals P into delta A by A plus Q into delta B by B plus R into delta C by C. Hence the rule, the relative error in a physical quantity raised to a power K is the K times the relative error in the individual quantity.